So welcome back to our investigation of Taylor's formula in the multivariate case. We have defined the notation in the last video, so we are now ready to define a Taylor polynomial and a Taylor series for multivariate functions. So let's have a look at the definition. As usual, we need a set X, subset of R to the n that is open. We have a point in that set, X star. That's the point where we want to define our Taylor polynomial. And we have a function that is k times continuously differentiable on X. And then we can define the kth Taylor polynomial of f at the point x star. Then the kth Taylor polynomial of f at x star is defined as, well, the notation is same as in the one-dimensional case. We denote that polynomial by tk f of x at x star, like this here. And it is defined as the sum of all vectors a in n0 to the n, where the absolute value of a is at most k. So the elements sum up to at most k. The highest combined degree that we get is k. And you remember in the one-dimensional case we had the nth derivative. So in this case what we do is we take the derivative dA of f at the point x star. So we replace that with all pure and mixed derivatives of degree a. We divide that by a factorial. And again, we replace the simple n factorial by a mixed factorial, possibly. And we multiply that with x minus x star to the power a. So again, a mixed power replaces the normal power n. Okay, so the formula looks very similar with that notation that we developed. It's just that we include all possible mixed differentials in that formula now. And of course, we can also define a Taylor series. That is just defined by letting the sum run over all possible vectors and not restricting the degree. And of course, that only works if f is actually infinitely often continuously differentiable. So for f in C infinity to the x, we can define a Taylor series. The Taylor series of f at x star is, well, that's t of f x star, and that's pretty much the same. The only difference is that we sum over all a in n0 to the n without restricting that choice further. The rest of the formula is the same. Okay, so that's the formal definition of Taylor polynomial. Hopefully easy to remember once you have memorized that notation here. Let's have a look at an example to see how that is applied. And we just continue the example from before so that we don't have to do all the work again. So you will remember we had a function f r2 to r defined as f of x1, x2. That was 3x1, x2 plus x1 squared minus 2x2 squared. Okay? Now let's see what we can do about the Taylor polynomial. We'll have a look at T2 f of x and x squared. So that means we'll sum up over all possible vectors a in n0 to the power 2, where the sum of the entries is less or equal to 2. So it can be 0, it can be 1, or it can be 2. Okay, let's treat these cases differently. So first we have the sums where a is equal to 0 of daf at x star over a factorial x minus x star to the power of a. Then we have the same sum, but now we're considering all those vectors where the sum is exactly equal to 1. Formula is the same. And finally, we'll consider those cases where the sum of the entries of the vector a is exactly equal to 2. Okay, so let's start with this expression here first. So you can hopefully see we investigated that case a equals, or the absolute value of a equals 0 already. We found that the only possible case here is that a equals the vector 0, 0. And basically what that means is the differential to that order is just the function itself. Yeah, and x to 0, 0 is just 1. And the factorial 0, 0 was 1 again. So what happens in this case is simply this becomes f of x star. Okay, then for the second part, let's investigate this part here. Now what we have here is the case is a equals 1, 0 and a equals 0, 1. So what we get is in both cases 1 over 1 factorial, then df dx1 at x star times x1 minus x1 star. And the second case is 1 over 1 factorial df dx2 at x star times x2 minus x2 star. Okay, so those are those two summands here. And finally, there is the case where the absolute value of a is 2. And that decomposes into three cases. We have a can be 2, 0, a can be 1, 1, or a can be 0, 2. So for the case 2, 0, that means we have 1 over 2 factorial d squared f over dx1 squared at x star times x1 minus x1 star squared. Then we have the mixed case, a equals 1, 1. That means we have 1 over 1 factorial 1 factorial d squared f over dx1 dx2 at x star times x1 minus x1 star times x2 minus x2 star, yeah, both to the power 1. And the last case, the vector 0, 2. So that's 1 over 2 factorial again, d squared f over dx2 squared at x star times x2 minus x2 star squared. Okay, so that's exactly what happens in this case, well, in general for any function f. So if we apply this to the function at hand, what happens here is we get first f at x star, so that's simply 3x1 star x2 star plus x1 star squared minus 2 x2 star squared. Then we have that blue part, so those two, we've computed those. That will yield 3x2 star plus 2x1 star, that is that derivative here, times x1 minus x1 star, plus, and the other derivative was 3x1 star minus 4x2 star times x2 minus x2 star. And finally, for the green part, we get plus 1 over 2 times 2, that was that derivative here, times x1 minus x1 star squared, plus the mixed derivative was 3, the factorial is 1, so that does not matter anymore, times x1 minus x1 star times x2 minus x2 star. And finally, we have 1 over 2 times minus 4, that derivative with respect to x2, 2 times, that was minus 4, times x2 minus x2 star squared. Okay, and you can see these Taylor polynomials tend to get quite long if you really write them down concisely. That's why these notations that we developed make things so much more convenient if you don't really have to express the actual numbers. Of course, you can also try to write this in vector matrix notation, and actually things become a lot more convenient if you do that. So that's something that does not just hold for this specific function, but in general for all Taylor polynomials of order 2. Yeah, all these can be expressed in the following way. That is always f of x star. That's always the 0th term. Then we have a term that involves the first partial derivatives. So in effect, we get something like the gradient that includes all of these, transposed times x minus x star. So we write this as a vector. It's a scalar product of two vectors. And then the quadratic term, that can also be written as 1 over 2 x minus x star transposed Hessian of f at x star times x minus x star. Okay, so it's a quadratic term with a matrix vector product in here. You might wonder where this 1 over 2 comes from. We have that, of course, we have that here and we have that here, but it does not appear here. But that's not a problem, because in the Hessian, that mixed term appears twice actually. Yeah, we have it in position 1, 2, and we have it in position 2, 1. So that term appears twice, and that means in this expression, the same term will turn up twice. Yeah, here. And that 1 over 2 kind of cancels out that doubling again, so we're back to the factor 1 over 1 factorial that we actually need. Okay, that concludes the example. Finally, to round this off, of course we have to talk about the approximation properties of Taylor's formula. And you will remember in the one-dimensional case we had this nice remainder theorem that gave us a formula to express the difference between the actual function and the Taylor approximation to some degree. And we could use that to compute the degree that we needed to achieve a certain approximation quality. And something like this also exists in the multivariate case. So we conclude with that theorem here. Oops. Sorry, wrong color. Okay, so that's also called Taylor's formula with remainder. It's kind of the most general case of a formula that you can have. As always, let x in R to the n be open. Let x star be in x. F, a function that is at least k plus 1 times continuously differentiable, because we need that k plus 1 for the remainder later. And now a condition that looks somewhat strange at first, but we'll talk about that in just a minute. We say let x be in x such that the line segment x star plus the interval 0, 1 times x minus x star is contained in x. Okay, what that means is the line segment connecting x star and x is completely contained in the set X. Okay, so how's that look like? Let's say if this here is your set X, yeah. Say the boundary is not included, so that's an open set. You have a point X star that may be here. You have a point X somewhere. For example, it could be here. And then, of course, the line segment between X star and X is this one. That's the line segment that we're talking about. So that would be completely contained in the set X. On the other hand, for a counterexample, if X was located here, and we have a look at that line segment, then this would obviously not be contained in X. Yeah, so that is not a subset of X. Okay, so the theorem works for that first setting with the green X, but it does not work for the setting with the red X. Okay, what does the theorem say actually? Let's formulate that as well. It says, then there exists some point x tilde that is contained on that line segment. So that is in x star plus 0, 1 x minus x star. And that means there is a lambda tilde in 0, 1 such that x tilde is exactly equal to x star plus lambda x minus x star. And you can see that the case lambda equals 0 corresponds to the point x star. The case lambda equals 1 corresponds to the point x, and any value in between is some point on that line segment. Okay, so there exists such a point such that, well, f of x, the function value, is equal to the Taylor polynomial of degree k at x star plus a remainder, and that remainder is precisely the Taylor formula evaluated at the point x tilde. Yeah, all the rest stays the same. And with the sum going over all a in n0 to the n, where the absolute value of a is exactly k plus 1. And that's why we need f to be k plus 1 times continuously differentiable. Okay, so this part here, this is the remainder in Taylor's formula. And you will hopefully remember in the one-dimensional case that looked exactly the same. Of course, the sum was not that complicated. We just took the k plus first derivative of f, evaluated at some point between x and x star. Only this time we need to make sure that this point actually is in x, so the function is actually defined on that point. That was not a problem in the one-dimensional case. Yeah, there's only one possibility to connect these two points. So if f was defined on an appropriate interval, then this would always be the case. It need not happen to be the case here in this multivariate setting. That's why we need that line segment condition on top of that. Otherwise, the formula is precisely the same. Okay, thanks a lot for your attention. This concludes our introduction of Taylor's approximation. Next, we are going to apply Taylor's approximation, same as we did in the one-dimensional case. The goal will be to compute local minima and local maxima and to characterize those. So we'll try to find a characterization of minima and of maxima, easy criteria that we can check to find which is which, and we'll use Taylor's formula for that purpose. So, goodbye, and I'll see you in the next videos.